All right, and welcome to Chapter 10, where we begin discussion of kinetics, in this particular case, chemical kinetics, with respect to the rates of reactions. So the branch of physical chemistry called chemical kinetics is concerned with the rates of chemical reactions. Chemical kinetics deals with how rapidly reactants are consumed and products are formed, how reaction rates respond to changes in the conditions of the presence of a catalyst, and the identification of the steps by which a reaction takes place. One reason for studying the rates of a reaction is the practical importance of being able to predict how quickly a reaction mixture approaches equilibrium. The rate might depend on variables under our control, such as pressure, temperature, the presence of a catalyst, and we might be able to optimize it by the appropriate choice of conditions. Another reason is that the study of reaction rate leads to an understanding of the mechanism of reaction, its analysis into a sequence of elementary steps. For example, we might discover the reaction of hydrogen and bromine to form hydrogen bromide proceeds by the dissociation of a Br2 molecule, the attack of a bromine atom on a hydrogen gas molecule, and several subsequent steps. By analyzing the rate of a biochemical reaction, we may discover how an enzyme, a biological catalyst, acts. Enzyme kinetics, the study of the effect of enzymes on the rates of reactions, is also an important window into how the macromolecules work. We need to cope with a wide variety of different rates, and a process that appears to be slow may be the outcome of many faster steps. That is particularly true in chemical reactions that underlie life. Photobiological processes like those responsible for photosynthesis and the slow growth of a plant may take place in about 1 picosecond. The binding of a neurotransmitter can have an effect after about 1 microsecond. Once a gene has been activated, a protein may emerge in about 100 seconds, but even that time scale incorporates many others, including the wriggling of a new formed polypeptide chain into a working conformation, each step of which might take about 1 picosecond. On a grander view, some of the equations of chemical kinetics are applicable to the behavior of whole populations of organisms, such as societal changes on time scales of 10 to the 7th or 10 to the 9th seconds. So, starting out with empirical chemical kinetics. The first step in the investigation of the rate and mechanisms of a reaction is the determination of the overall stoichiometry of the reaction and the identification of any side reactions. The next step is to determine how the concentrations of the reactants and products change with time after the reaction has been initiated. Because the rates of chemical reactions are sensitive to temperature, the temperature of the reaction mixture must be held constant throughout the course of the reaction, for otherwise the observed rate would be a meaningless average of the rates for different temperatures. The method used to monitor the concentrations of reactants and products and their variation with time depends on the substances involved and the rapidity with which their concentration changes. For example, you can look at a variety of different types of analyses in Table 10.1. We'll see that spectrophotometry, the measurement of the absorption of light by a material, is used widely to monitor concentration. If a reaction changes the number or type of ions present in solution, then concentrations may be followed by monitoring the conductivity of the solution. Reactions that change the concentration of hydrogen ions may be studied by monitoring the pH of the solution with a glass electrode. Other methods of monitoring the composition include the detection of light emission, titration, mass spectrometry, gas chromatography, and magnetic resonance, including NMR. Polarimetry, the observation of the optical activity of a reaction mixture, is occasionally applicable. So, let's talk about spectrophotometry briefly. The key result for using the intensity of absorption of radiation at a particular wavelength to determine the concentration of the absorbed species is the empirical Beer-Lambert law. In this expression, I0 and I are the incident and transmitted intensities, respectively, and L is the length of the sample through which the light has the ability to pass through. The ratio of the transmitted intensity I to the incident intensity I0 is called transmittance, or T, of the sample, where transmittance is the ratio of I over I0. The quantity, epsilon, is called the molar absorption coefficient, or molar absorptivity coefficient. It's also been known previously as the extinction coefficient. It depends on the wavelength of the incident radiation, and it's greatest where the absorption is most intense. The unit for epsilon are typically cubic decimeters per mole per centimeter, which are sensible when J is expressed in moles per cubic decimeter and L in centimeters. The dimensionless expression on the right of equation 10.2 is called the absorbance, A, of the sample, also formerly known as optical density. We measure the absorbance of a sample by selecting an appropriate wavelength, measuring the incident and final intensities of wavebeam, and using equation 10.1 in the form where absorbance equals the log of the ratio of I naught over I, or the negative log of transmittance. Once we know the absorbance of a sample, we determine the concentration of the absorbent species and follow its change with time by using the form below in equation 10. In real-time analysis, the composition of a system is analyzed while the reaction is in progress by direct spectroscopic observation of the reaction mixture. In the flow method, the reactants are mixed as they flow together in a chamber. The reaction continues as the thoroughly mixed solution flows through a capillary outlet tube at about 10 meters per second. And different points along the tube correspond to different times after the start of the reaction. Spectrophotometric determination of the composition at different positions along the tube is equivalent to the determination of the composition of the reaction mixture at different times after being mixed. The technique was originally developed in connection with a study of the rate at which oxygen combined with hemoglobin. Its disadvantage is that a large volume of reactant solution is necessary, as the mixture must flow continuously through the apparatus. This disadvantage is particularly important for reactions that take place very rapidly because the flow must be rapid if it's to spread the reaction over an appreciable length of tube. The stopped flow technique avoids this disadvantage, and is visualized in figure 10.3 below. The two solutions are mixed very rapidly, in less than a millisecond, by injecting them into a mixing chamber designed to ensure that the flow is turbulent and the complete mixing occurs very quickly. Behind the reaction chamber, there's an observation cell fitted with a plunger that moves back as the liquid floods in, but that comes up against a stop after a certain volume has been admitted. The filling of the chamber corresponds to the sudden creation of an initial sample of the reaction mixture. The reaction then continues to be in the thoroughly mixed solution and is monitored spectrophotometrically. Because only a small, single charge of the reaction chamber is prepared, the technique is much more economical than the flow method. The suitability of the stop flow technique to the study of small samples means that it is appropriate for biochemical reactions, and it has been widely used to study the kinetics of enzyme action. Modern techniques of monitoring composition of spectrophotometrically can span repetitively a wavelength range of 300 nanometers at 1 millisecond intervals, meaning that you can scan over a range of different wavelengths so quickly that within reasonable resolution, you can scan for the absorbance and transmittant changes at a variety of wavelengths simultaneously for even relatively rapid reactions. Now, very fast reactions can be studied by flash photolysis, in which the sample is exposed to a brief flash of light that initiates the reaction, and then the contents of the reaction chamber are monitored spectrophotometrically. Lasers can be used to generate nanosecond flashes routinely, picosecond flashes quite readily, and flashes as brief as a few femtoseconds in special arrangements. Fast reactions are also studied by pulse radiolysis, in which the flash of electromagnetic radiation is replaced by a short burst of high velocity of electrons. In contrast to real-time analysis, quenching methods are based on stopping or quenching the reaction after it's been allowed to proceed for a certain time, and the composition is then analyzed at leisure. The quenching of the entire mixture or sample drawn from it can be achieved either by cooling suddenly or by adding the mixture to a large volume of solvent, or by rapidly neutralizing an acid reagent. The method is suitable only for reactions that are slow enough for there to be little reaction during the time it takes to quench the mixture. So, talking about reaction rates. The raw data from experiments to measure reaction rates are quantities such as the absorbance of a sample that are proportional to the concentrations or partial pressures of reactants and products at a series of times after the reaction is initiated. Ideally, information on NA intermediates should also be obtained, but often they cannot be studied because their existence is so fleeting that the concentration is effectively low. More information about the reaction can be extracted if data are obtained at a series of different temperatures. The next few sections look at these observations in more detail. So, the definition of rate. The rate of reaction taking place in a container of fixed volume is defined in terms of the rate of change of the concentration of a designated species, J perhaps, where change in the concentration of J is the change in the molar concentration of species J that occurs during the time interval delta T. And that is shown here, where rate equals the change in concentration of J over a designated interval of time. So you end up with a change in concentration per unit time, which is our rate. We've put the change in concentration because modulus sign to ensure that all rates are positive. If J is a reactant, its concentration will decrease, and if delta J will be negative, but delta J with absolutes around it is of course positive. Because the rates at which reactants are consumed and products are formed change in the course of a reaction, it's necessary to consider the instantaneous rate of the reaction, its rate at a specific instant. The instantaneous rate of consumption of a reactant is the slope of the graph of its molar concentration plotted against time, with the slope evaluated as the tangent to the graph at the instant of interest, which is what we're looking at in figure 10.4 above. The rate of chemical reaction is the slope of the tangent to the curve, showing the variation of concentration of a species with time. The graph is just a plot of the concentration of reactant, which is consumed as the reaction progresses. The rate of consumption decreases in the course of the reaction as the concentration of reactants decrease, making it less probable for them to collide with one another, therefore slowing the rate of reaction. The instantaneous rate of formation of a product is also the slope if the tangent to the graph of its molar concentration plotted, and also reported as a positive quantity. The steeper the slope in either case, the greater the rate of reaction. With the concentration measured in moles per cubic decimeter and time in seconds, the reaction rate is reported in moles per cubic decimeter liter per second. From now on, we shall denote the instantaneous rate as V for velocity. So, a brief comment. The slope of the tangent to plot of concentration of J against time curve at any instant is expressed mathematically as the magnitude of the derivative, where the interval delta T, and consequently the change in concentration of delta J, has been allowed to become infinitesimal. Therefore, the precise definition of reaction rate is as follows, where you have the derivative of the delta J with respect, or of J with respect to time. In general, reactants in a given reaction are consumed at different rates, and the various products are also formed at different rates. However, these rates are related by the stoichiometry of the reaction. For example, in the decomposition of urea, what we see here, in an acidic solution, you have aqueous urea, where you have one equivalent of urea reacts with two equivalents of water, yielding two equivalents of ammonium plus one equivalent of carbonate. The rate of formation of ammonium is twice the rate of the disappearance of urea because for 1 mole of urea consumed, 2 moles of ammonium is formed. Once we know the rate of formation or consumption of one substance, we can use the reaction stoichiometry to deduce the rates of formation or consumption of the other participants in the reaction. In this example, for instance, the rate of formation of ammonium would equal 2 times the rate of consumption of urea. One consequence of this kind of relation is that we have to be careful to specify exactly what species we mean when we report rate. There is a complication. If the reactants form a slowly decaying intermediate, which we'll see an example later, then the products do not form at the same rate as the reactants turn into the intermediate. In such cases, we have to be very careful about the interpretation of the measured rate of reaction. This complication can be turned to an advantage, though. The observation that the consumption and formation rates are not related by the reaction stoichiometry is a good sign that a long-lived intermediate is involved in the reaction. So, on to rate laws and rate constants. An empirical observation of the greatest importance is that rate of reaction is often found to be proportional to the molar concentration of the reactant raised to a simple power. For example, it may be found that the rate of reaction is directly proportional to the concentrations of reactants A and B. So in this particular case, the rate of reaction would equal K sub R, which is the characteristic of the reaction being studied called the rate constant or rate coefficient, times the concentration of A times the concentration of B. The rate constant is independent of the concentration of the species taking part in the reaction, but depends on the temperature. An experimentally determined equation of this kind is called the rate law for the reaction. More formally, a rate law is an equation that expresses the rate of reaction in terms of the molar concentrations, or partial pressures, of the species in the overall reaction, including possibly the products and any catalyst that might be present. The units of K are always such as to convert the product of concentrations into a rate expressed as a change in concentration divided by time. For example, if the rate law is one shown above, with concentrations expressed in moles per decimeter cubed, then the units of K will be decimeter cubed per mole per second, because of the following rationale. Now, one other really important thing we need to point out is that now, because of rate, we're dealing with small k. We, of course, just finished talking about equilibrium, which had big K. Those two Ks are not interchangeable because the discussion of equilibrium and rate are not interchangeable. They're complementary. Remember, equilibrium, big K, little k, rate. In gas phase studies, including studies of the processes taking place in the atmosphere, concentrations are commonly expressed in molecules per cubic centimeter. So the rate constant for the reaction above would be expressed in cubic centimeters per molecule per second. We can use the approach just developed to determine the units of the rate constant from the rate law in any form. For example, the rate constant for a reaction with rate law of the form K times concentration A is commonly just expressed as per second. A quick illustration. Go ahead and take a second to read through this example, which illustrates how for different rate laws you can deduce the specific units associated with its rate constant. Now, once we know the rate law and the rate constant of the reaction, we can predict the rate of reaction for any given composition of the reaction mixture. We shall see that we can use a rate law to predict the concentration of the reaction and products at any time after the start of the reaction. Furthermore, a rate law is also an important guide to the mechanism of the reaction, for any proposed mechanism must be consistent with the observed rate law. Now, on to reaction order. A rate law provides a basis for the classification of reactions according to their kinetics. The advantage of having such a classification is that the reactions belong to the same class, have similar kinetic behavior. Their rates and the concentration of the reactants and products vary with composition in a similar way. The classification of reactions is based on their order, the power to which the concentration of a species is raised in the rate law. For example, a reaction with rate law in equation 10.6, where the velocity of a reaction equals K times the concentration of A times the concentration of B, is first order in A and first order in B, because the exponent to which it's raised for both A and B are 1. A reaction with rate law where rate equals K times the concentration of A squared is second order with respect to A. The overall order of a reaction with rate law of the form rate equals K times the concentration of A raised to A, the concentration of B raised to B, the concentration of C raised to C, etc., is the sum of the exponents A plus B plus C of the orders of the components. The two rate laws just quoted both correspond to reactions that are second order overall, because the first was first order with respect to A to B, but that means overall it's 1 plus 1, or second order overall. In the second example, it was A squared, which is also second order. An example of the first type of reaction is the reformation of a DNA double helix after the double helix has been separated into two strands by raising the temperature or pH. This reaction is first order in each strand and second order overall. An example of the second type is the reduction of nitrogen dioxide by carbon monoxide, where the rate equals K times the concentration of nitrogen dioxide squared. This is second order in nitrogen dioxide, and because no other species occurs in the rate law, second order overall. The rate of the latter reaction is independent of the concentration of carbon monoxide, provided that some carbon monoxide is present. This independence of concentration is expressed by saying that the reaction is 0th order in carbon monoxide, because the concentration raised to the power of 0 is simply 1. So concentration of carbon monoxide raised to 0 equals 1, and it fundamentally falls out of the equation. A reaction needs not have an integral order, and many gas phase reactions do not. For example, if a reaction is found to have the rate law where rate equals K times the concentration of A to the 1/2 power times B to the first, then it's half order in A, first order in B, and 3/2 order overall. If a rate law is not of the form rate equals K, A raised to A, B raised to B, C raised to C, etc., then the reaction does not have an overall order. Thus, experimentally determined rate law for the gas phase reaction, where hydrogen gas plus bromine gas react to form two equivalents of hydrogen bromide, is described as follows. Although the reaction's first order in hydrogen, it has an indefinite order with both respect to bromine gas and hydrogen bromide, and an indefinite order overall. Similarly, a typical rate law for the reaction of an enzyme E on substrate S that we'll see in Chapter 11 is as follows, where Km is a constant, which is our Michaelis-Menten constant. And for those of you who've had biochemistry, you'll recognize some of what you're looking at now. But we'll get to this later, like I said, in Chapter 11. This rate law is first order in the enzyme, but does not have specific order with respect to the substrate. Under certain circumstances, a complicated rate law without an overall order may simplify into a law with a definite order. For example, if the substrate concentration in the enzyme catalyzed reaction is so low that the concentration of substrate is much, much less than the Michaelis-Menten constant, then we can ignore the concentration of S in the denominator of the equation 1010, which just simplifies to the following, where the rate is going to equal the rate constant over the Michaelis-Menten constant times the concentration of substrate times the concentration of enzyme, which is first order in respect to substrate, first order in respect to enzyme, and second order overall. It's very important to note that a rate law is established experimentally and cannot, in general, be inferred from the chemical equation of reaction. To reiterate that, rates must be established experimentally because we cannot infer from the type of reaction necessarily what the rate law would be. The reaction of hydrogen and bromine, for example, has a very simple stoichiometry, but its rate law is very complicated. That's why you never see that particular one listed in a 100-level textbook. In some cases, however, the rate law does happen to reflect the reaction stoichiometry. This is the case with the reaction of hydrogen and iodine, interestingly, which had the same stoichiometry as the reaction of hydrogen and bromine, but a much simpler rate law. So, the determination of rate law. The determination of rate law is simplified by the isolation method, in which all the reactants except one are present in large excess. We can find the dependence of the rate on each of the reactants by isolating each of them in turn, by having all the other substances present in large excess and piecing together a picture of the overall rate law. For instance, we might use methyl iodide in solution at a concentration of 0.2 moles per cubic decimeter and an attacking nucleophile at only 0.01 moles per cubic decimeter. If a reactant B is in large excess, for example, it's a good approximation to take its concentration as constant throughout the reaction. Then, although the true rate law might be, say, rate equals the rate constant times the concentration of A times the concentration of B squared, we can approximate B by its initial value, B naught, from which it hardly changes over the course of the reaction, and simply write the following. Because the true rate law has been forced into first-order form by assuming a constant B concentration, the effective rate law is classified as pseudo-first-order, and the effective rate constant is called the effective rate constant for a given fixed concentration of B. If instead the concentration of A were in large excess and hence effectively constant, then the rate law would simplify to the rate equals the effective rate law times the concentration of B squared, where A is fundamentally equal to its initial value and held constant. This pseudo second order rate law is also much easier to analyze and identify than the complete law. Note that the order of the reaction and the form of the effective rate constant change according to whether A or B is the one in excess. In a similar manner, a reaction may even appear to be zeroth order. For instance, the oxidation of ethanol to acetaldehyde by NAD+ in the liver in the presence of the enzyme liver alcohol dehydrogenase is as follows, where ethanol plus NAD plus water reacts to form acetaldehyde plus NADH plus hydronium or acid. This reaction is zeroth order overall as the ethanol is in excess and the concentration of NAD+ is maintained at a constant level by normal metabolic processes. So although it's being consumed, it's also being replaced by other processes. Many reactions in aqueous solution that are reported as first or second order are actually pseudo-first or pseudo-second order. The solvent water participates in the reaction, but it's in such large concentration that its concentration fundamentally remains constant. In the method of initial rates, which is often used in conjunction with the isolation method, the instantaneous rate is measured at the beginning of the reaction for several different initial concentrations of reactants. For example, suppose the rate law for a reaction with A is isolated is as follows, where the rate equals the rate constant times the concentration of A raised to A. Given that, then the initial rate of the reaction, V naught, is given by the initial concentration of A, where the initial rate equals the rate constant times the initial concentration of A raised to A. Taking logarithm gives the following. And this equation has the form of the equation for a straight line when rearranged, so that the log of the initial rate equals the log of the effective rate constant plus A times the log of the initial concentration of A. It follows that for a series of initial concentrations, which we can model experimentally, a plot of the logarithms of the initial rates against the logarithms of the initial concentrations of A should be a straight line, and that the slope of the graph will be A, the order of the reaction with respect to species A. And that's what we're seeing here in figure 10.5. The plot of the log of the initial velocities against the log of initial concentrations gives straight lines with slopes equal to the order of the reaction rate. Order of the reaction. The method of initial rates might not reveal the entire rate law, as in a complex reaction that produces them. Products themselves might affect the rate. That is the case for the synthesis of hydrogen bromide, which we showed earlier. However, it's particularly useful for simpler reactions, which account for a substantial amount of the chemistries that we'll be dealing with. So let's work through an example quickly. What I want you to do is take the moment, pause this video, and work through this particular example of calculating experimentally what the rate law for this given set of data indicate. So go ahead and pause it, work through, and then go ahead and hit go. And now we're back to integrated rate laws. A rate law tells us the rate of the reaction at a given instant when the reaction mixture has a particular composition. That is, rather than being given the speed of a car at each point of its journey. For a car journey, we may want to know the distance that a car has traveled at a certain time given its varying speed. Similarly, for a chemical reaction, we may want to know the composition of the reaction mixture at a given time, varying the rate of the reaction. An integrated rate law is an expression that gives the concentration of species as a function of time. Integrated rate law has two principal uses. One is to predict the concentration of species at any time after the start of the reaction. Another is to help find the rate constant and order of the reaction. Indeed, although we have introduced rate laws through a discussion of the determination of reaction rates, these rates are rarely measured directly because the slopes are so difficult to determine accurately. Almost all experimental work in chemical kinetics deals with integrated rate laws. Their great advantage being that they're expressed in terms of the experimental observables of concentration and time. Computers can be used to find the integrated form of even the most complex rate laws numerically, and in some cases can be used to obtain closed algebraic expressions. However, a number of simple case solutions can be obtained by elementary techniques and proven to be very useful. For chemical reaction and first-order rate law of the form where A reacts to form products, rate of consumption of A equals the rate constant K times the concentration of A. We show in derivation in the text, derivation 10.2, that the integrated rate law is as follows. So if you're interested in the origins of rate laws, go ahead and grab the text and take a look at the derivations. If you're not interested in derivation, you still need to be able to understand which rate laws apply and know them. So in this particular case, the integrated rate law would be the natural log of the ratio of the initial concentration of A over the concentration of A, and that's going to equal the rate constant times time. Two alternative forms of the expression are as follows. Notice that the first equation, 1013b, conforms to the variation of the equation y equals mx plus b. and can be used experimentally to find these different terms. Now, equation 1013c has the form of an exponential decay. A common feature for all first-order reactions, therefore, is that the concentration of the reactant decays exponentially with time. Equation 1013c, the one that indicates exponential decay, lets us predict the concentration of A at any time after the start of the reaction. Equation 13b shows us that if we plot a natural log of A against T, then we'll get a straight line if the reaction is first order. If the experimental data do not give a straight line when plotted this way, then the reaction is not first order. If the line is straight, then it follows from equation 13b that its slope is equal to negative k. So we can also determine the rate constant for the graph. Some rate constants determined in this way are given in table 10.2 below. Now, if you have any ambiguity on what we just discussed, there's a really nice example, 10.2, right here on the rest of the slide to the right, and I encourage you to pause the video here and work your way through this example to help clarify what we just talked about. Now, we need to see how the concentration varies with time for reaction and second order rate law if the form A goes to products and the rate of consumption of A equals K times the concentration of A squared. As before, we suppose that the concentration of A at time equals 0 is initial concentration of A, or A naught, and as shown in derivation 10.3 in the text, once again, find that the following, where you're now looking at inverses versus logarithmic transforms, where now for second order you have 1 over the concentration of A equals 1 over the initial concentration of A plus KT. This can also be written as following in 1015b. Now 1015a shows that to test for a second order reaction, we should plot the inverse of the concentration of A against time and expect a straight line. If the line is straight, then the reaction is second order in A, and the slope of the line is equal to the rate constant. Some rate constants determined in this way are given in table 10.3, which will be on the next slide. Equation 1015b, the rearranged version, enables us to predict the concentration of A at any time after the start of the reaction. From plots of concentration of A against T, we see that the concentration of A approaches 0 more slowly in a second order than in first order reaction with the same initial rate. That is, reactants that decay by second order process die away more slowly at low concentrations than would be expected if the decay was first order. A point of interest in this connection is that pollutants commonly disappear by second order processes, so it takes a very long time for them to decline to acceptable levels. Table 10.4 summarizes integrated rate laws for a variety of simple reaction types. So, here are the two tables, including the summary of integrated rate laws in table 10.4 for different orders of reactions. So we have the rate laws and integrated rate laws for 0, first, and second order laws, and for second order laws, reaction types of where A goes to products and A plus B goes to products. So now that we have covered all of that, we're able to start discussion of half-lives and time constants. But this also puts us at nearly 40 minutes of lecture time, and we're halfway through the chapter. So we're going to take this time to pause the video. I'm going to upload this section, and then I'll pick up with the second half of the chapter. So we'll pick up the second half of chapter 10 with half-lives.